Good morning students, myself Vaidehi working as Assistant Professor in Sri Muthukumaran Institute of Technology. Today the video lecture is from the subject EC 3452 EMF. In this lecture we will discuss the fundamental concept of magnetostatics. Magnetostatic is the study of magnetic fields produced by steady currents. The topics covered include Lorentz force, Ampere circuit law, vector magnetic potential, Biot-Savart law, magnetic field intensity and relative permeability. These concepts form the basis for understanding transformers, motors, generators and other electromagnetic devices. Next we see about the learning outcomes. At the end of this lecture, students should be able to explain the force experienced by charged particles in magnetic field, apply Ampere's and Biot-Savart laws for magnetic field calculations, understand the significance of vector magnetic potential and define magnetic field intensity and relative permeability. These concepts are important for both theoretical understanding and engineering applications. Next we see about the Lorentz force equation. Let us begin with the Lorentz force equation. This equation describes the force experienced by a charged particle moving in electric and magnetic fields. The equation is F is equal to Q into E plus V cross B, where F is the force, Q is the charge, E is the electric field intensity, V is the velocity of the charged particle and B is the magnetic flux density. The magnetic force component is always perpendicular to both the velocity and magnetic field directions. Therefore, the magnetic field changes the direction of motion but does not change the speed of the particle. Applications of Lorentz force include particle accelerators, cathode ray tubes, mass spectrometers and electric motors. Ampere's circuit law relates magnetic fields to the current producing them. It states that the integral of magnetic field intensity around a closed path is equal to the current enclosed by that path. Mathematically, integration of H dot dl is equal to I enclosed. This law is especially useful when dealing with symmetrical structures such as long straight conductors, solenoids and toroids. Using Ampere's law, we can determine magnetic field intensity without performing complex integrations. The law plays a role similar to Gauss law in electrostatics. Next we see about the vector magnetic potential. It is represented by the symbol A. Magnetic flux density B can be expressed as the curl of vector potential A. B is equal to del cross A. The vector magnetic potential is useful because it simplifies the solution of many electromagnetic problems, especially in numerical simulations and advanced electromagnetic analysis. Although magnetic flux density B is a measurable quantity, vector potential A is often used as an intermediate mathematical tool for easier calculations. This concept becomes very important in antenna theory, wave propagation and computational electromagnetics. Next we see about the Biot-Savart law. Biot-Savart law provides a method to calculate the magnetic field produced by a small current element. The differential form of the law is dB is equal to nu by 4 pi into IDL into R cap divided by R square. According to this law, magnetic field increases with current. Magnetic field decreases with distance. The direction is determined using the right hand rule. Biot-Savart law serves as the fundamental law for magnetic field calculations and is analogous to Coulomb's law in electrostatics. Next, the applications of Biot-Savart law. Using Biot-Savart law, we can derive expressions for magnetic fields generated by various current distributions. Examples include a long straight conductor carrying current, a circular current loop, a solenoid consisting of multiple turns, electromagnetic devices such as motors and actuators. Understanding these applications allows engineers to design devices with desired magnetic field strength and distributions. Next we see about the magnetic field intensity. Magnetic field intensity is represented by H and is defined as the magnetizing force responsible for producing magnetic flux. The relationship between magnetic flux density and magnetic field intensity is H is equal to B by nu, where B is magnetic flux density and nu is permeability. The SI unit of H is ampere per meter. The magnetic flux intensity depends on the source current and geometry, whereas magnetic flux density also depends on the material properties. This distinction is important when analyzing magnetic materials. Next we see about the relative permeability. Relative permeability indicates how easily a material supports magnetic flux compared to free space. It is defined as nu r is equal to nu by nu naught, where nu is the permeability of the material and nu naught is the permeability of free space. For air, relative permeability is approximately 1. For magnetic materials such as iron, the value can be several hundred or several thousand. Materials with a higher relative permeability allow magnetic flux to pass more easily and therefore widely used in transformer cores and electrical machines. Next we see about the comparison and the summary of this lecture. Let us summarize the key concepts covered in this lecture. Lorentz force explains the force acting on moving charges in electric and magnetic fields. Ampere's law relates magnetic field intensity to enclosed current. Biot-Savart law provides a method for calculating magnetic fields due to current elements. Vector magnetic potential offers a mathematical approach for analyzing electromagnetic fields. Magnetic field intensity represents magnetic force. Relative permeability indicates how easily a material supports magnetic flux. Together, these concepts provide the foundation for understanding electromagnetic devices and magnetic field analysis. Thank you for your attention. Hope you all understood the concepts. We will see in the next video.